something. I'm looking. I'm gonna check. What's up? Yeah. One time I gave an astronomy on talk, and I got off the stage, and everybody was clapping, and I was like, "They love me." And they were like, "You just said that on air." I'm like, "Well, they did."
Like I'm just speaking truth.
Yeah, I stand by what I said.
Oh, this is
That's all.
audio.
Oh, okay. They love me.
Okay, 0 viewers. And the thumbnail is Charlie Willis.
So, like, all of them.
They already are.
Like a talk on all like the joke papers. That would be so funny.
Like, on all of like the tradition that we Man, if you want to give me an AOT to talk about rats, I'll do it.
Oh yeah, you can, sure. What are you doing next month?
Talking about the rats, baby.
Talking about rats, babe?
Who hasn't read an April Fool's paper about rats? I mean,
Oh yeah.
it's 7 pages of fuel. I'm gonna start doing proper audio thing.
Do your thing. Okay, bring your trivia sheets and your golf pencils up to Chester at the front, who is going to collect them, and we will grade them. Do it now. I feel like more of you did trivia than are getting up at the moment. No?
I did not. I did
I
not.
will happily grade yours.
I don't know. No.
Conflict of I just want to jump.
Any conflict of interest.
I got 10.
You got number 10? I mean, I would have been disappointed.
So false and so upset I saw it in your bio.
It's in my bio.
You said in the picture I posted.
Okay, has everybody turned in their trivia sheets yet? Am I talking to myself up here? Yeah, wait, ready? That's so good. Okay. Alright, so we have all of the trivia, I am assuming, which means we're going to get on with grading, and we're also going to move on to the first talk. Okay, enough stalling for time. So I'm going to introduce the first speaker of the evening. Her name is Sam Garza. She's going to be talking about space as a soup and she is a fork. And I will let her elaborate on why that is. But Sam, I just want to talk about Sam for a second. Sam is a fourth and final year PhD candidate at the University of Washington. As you know, she's defending, because I already said that. Sam's also my roommate. And she has been running the social media for Astronomy on Tap for the last 3+ years. We've been doing it together. So sad. We're having our moment together. This is so sad. So you guys should all be really appreciative towards her, and listened to her talk. And I appreciate Sam a lot. So with that, I'm going to bring her up on stage.
Thanks for that introduction. It's going to be a preface for what's going to happen on Friday. I've already practiced my talk, and I cry every time when I talk about being in my talk, so it's mutual. But anyway, I'm here to talk to y'all about how space is a soup, and I'm a fork, and I just want to highlight this picture here that actually made for me, which is kind of the vibe that I had my entire graduate career of I'm just very confused as I'm looking at my data. But hopefully I'll be less confused because I have to sound confident on Friday, but keep this in mind as this is the vibe. But silliness aside, before we talk about galactic atmospheres, which my research is on, I want to kind of orient us and ask the question of where we are in the galaxy. And you can start really simple. We're all here together at a brewery. That's where we are, duh. But I was thinking more along the lines of this, where we're in Seattle, Washington, we're on the United States of America, but really on this planet Earth. And if you keep zooming out, you'll see that we're just if we zoom, thank you. Oh, we zoomed too fast. We zoomed out. We're just one planet in the solar system surrounding our sun. And if you keep moving out further, the next thing that you would encounter is Alpha Centauri. This is a triple star system. It's about 1.5 light years away. But what's really cool about this picture, and I don't know if you can see it very well, is that there's a ton of material that's between stars. And this is what we call the interstellar medium. It's really pretty. It's mostly made up of hydrogen gas and helium and a little bit of dust. Dust is important if you have the trivia. It could be a little nasty. But there's an answer for you. But this is what's really important. If you build up more and more of this interstellar medium and you zoom out further, you get our galaxy. And this is where we are. The yellow star is where we are. We're about 26 light years from the center of the galaxy. And this is what we look like, or what we think we look like. We can't actually observe what our own galaxy looks like because we're inside the plane, which makes all of it hard to study, which I know there's a better answer for the trivia, which we'll find out later, but all of it's really hard to study. And it was the Milky Way where I actually fell in love with galaxies. I did my first research internship studying the inner part of the galaxy, the near and far 3 kiloparsec arms. And these images are of the interstellar medium that we were talking about. This one's in the far arm. It's got a nice little bubble over here. This one's in the near arm. You can see some pretty stars in there. It's got a nice shape. This one was my favorite one. I looked at a billion of these, but these are just some examples. And this is where I literally fell in love with galaxies, and I wouldn't be here without this internship that I did. And then I kept studying them and kept moving from looking at star formation, specifically the ISS and just the Milky Way, but also to a bunch of galaxies. And this is I did at the National Radio Astronomy Observatory, and I was doing a survey called Degas. And when my advisor first told me I was going to be looking at Degas, I was like, Degas? This Degas? And she's like, no, we're not doing art history, and I got a little sad. We're looking at this Degas. It stood for Dense Extragalactic GBT plus Argus Survey. I know that's a mouthful. GBT stands for the Green Bank Telescope. I actually got to stand on this telescope. It's one of the largest freestanding rotating radio dishes. So I have a little hard hat. It's a funny picture. I should have put it in here. And then Argus is the instrument that we use to look at these galaxies, and it created these images of them. And so you can see, looking at different spectra or different parts of the electromagnetic spectrum, you get different images. So looking at it in kind of this darker fuzzy range, but then you can also get really, really pretty images looking at that dust, interstellar medium, and specifically that dense gas. So I kept looking at different aspects of galaxies, different dusts. I then moved to studying the Whirlpool Galaxy, which is a spiral galaxy. If y'all didn't mark spiral galaxy, I'm gonna be a little sad. But this is my favorite galaxy. Look how pretty she is. I don't know if she's coming out very well.
Better than before. Yeah.
All right. This is a better projector. We talked about this last month, but it's still light outside. This is the Whirlpool Galaxy. I'm hoping my next image shows up really well, but essentially, what I want you to see from this image is, I don't want to trip. I have a lot of tripping in my life. There's these really pretty, pink parts in here, and those are giant molecular clouds. So we moved from looking at interstellar medium, hydrogen clouds, to looking at giant bubbles, where they're big stellar nurseries. And this is what's really, really important that I want to focus on, and let's see if this works. So we're going to look at it a little differently. It's going to move, hopefully. This isn't coming out the way I wanted to, but basically we're looking at the Whirlpool Galaxy in 3D, which we typically don't get to do a lot of the time, and it's really sick to look at it this way. And so what you're seeing is the inner part. This is mapped with radio data, and the red points, if they're coming out correctly, those are all giant molecular clouds. That is where stars are forming actively, which there's tons of these all over the galaxy. And the rest of the colors there are kind of like other parts of molecular gas. And I really, really like looking at this because you get to see it in a way that you never really get to typically. And it's fun to look at this. And so this is all my undergraduate career, and there's a reason why I'm showing you all this stuff, but I moved from studying the gas inside of a galaxy into when I came to graduate school, looking at the gas outside of galaxies. So here we are, we finally made it to our title. You're like, Sam, gosh, that's a lot of background. Why did we talk about this stuff? No, it's important because stars are the building blocks of life, and they're the reason for a lot of what I study and how the things that get out into space get there. And those are our cosmic ingredients. They don't look like this, it's very, very silly. But this is kind of what I did think about. And if you go back to me looking at soup, I'm looking at soup here, okay? There's all sorts of stuff in here. I don't know what's in here. But this is the thing that we're looking at. And before I keep telling you more about these galactic atmospheres, I want to take a step back and be like, why do you even research this? Because you're getting your PhD, but why? Why should you care about galactic atmospheres? Well, one, there's a lot of gas in the atmospheres, and if you care about planets and stars, maybe you like life out in the universe, you want to study exoplanets like Megan does, if you just care about stars in general, maybe binary stars like Tom, you need gas to form stars. And one of the ways you can get gas is actually through galactic atmospheres. So it's really, really important to understand these processes that are happening in them so that we can get more and more stars in our galaxies. Another question that you can start to think about with galactic atmospheres is figuring out why galaxies stop forming stars. This is something that we actually don't understand fully, why they become quenched or red and dead. And so one of the ways we think that internal processes that are happening in there, whether it's like gas cooling down, gas heating up, can cause these galaxies to stop having enough fuel to actually form stars. So they're really, really important to study. And also, this is also an important question, is why do galaxies lack their share of visible material? You might have seen this pie chart before. It's where the visible matter only in the entire universe makes up about 3 to 5%, and everything else is dark energy and dark matter. And so we're still investigating this. You've maybe seen a lot of cosmological talks and things, but the better constraints that we get on the visible matter, and especially halos of galaxies, can tell us a lot about what's going on in this pie chart. So my research has value. I think it's cool if I might convince you. But let's actually talk about this research and exactly what are galactic atmospheres. So this is my artistic representation of what a galactic atmosphere would look like. For the more technical term, it's called the circumgalactic medium, the CGM. That might have been, I think, one of the questions. But anyway, this animation shows the complexities that's happening in there. So originally I showed you as these kind of like fluffy clouds, and it's just like stagnant, just an atmosphere. No, there's a ton of stuff going on. You've got gas falling into the galaxy, either through external processes, and it's just cooling and coming on in, just like a conveyor belt almost. You've got gas being blown out of the galaxy through those stars that we talked about. They die in these super dramatic deaths, and they push material out into the galaxy. And then all this gas kind of like mixes together in this soup and falls back onto the galaxy. So these super complex places. And if you pause at the end, here we go, you can see all those parts together and all the labels in there. And I want to also mention that these things are huge. They're on the orders of hundreds of thousands of light years across. They're these massive, massive halos that are just surrounding our galaxies. So there's a lot of things to study in here. And again, I was mentioning those stars. Those are the ones that push these elements out there. And the ones that I specifically care about are, there you go, oxygen, nitrogen, silicon, and especially carbon. We're going to be talking about carbon a lot. And you get these elements from stars. And so to figure out that process, I'm going to zoom back in here for a little bit. Oh, and I forgot their ingredients. These are our ingredients that we're going to be using. So if we zoom back in here, back into our galaxy. Now here I have a diagram of your stellar life cycle. I have conveniently left off the binary stars because that's the next talk. I didn't want to spoil anything about binary stars. But this is how we get our stars. We start from those giant molecular clouds that we were talking about. We move into kind of protostellar disks. And as these stars or these giant clouds are kind of collapsing and condensing, the more and more that they condense down, you get a star. It's kind of fighting against the battle between pressure and forgetting words. Pressure and gravity. Gravity is the word. I believe I forgot gravity. But essentially, as soon as that happens and you start forming a star, you're fusing hydrogen into helium. And that process can stand for a really, really long time. We call that the main sequence. Our sun is a main sequence star. They're really chill. But we don't care about main sequence stars as much. We care about how they die. Dying is really cool. If you're it is. It's a journey. So when he loses the battle between pressure and gravity, I didn't forget it again, there we go, then the core contracts even further and the outer parts puff up. And in this process is when you start getting those heavier elements that I care about, like carbon, nitrogen, oxygen, all those things. And so those keep burning through and burning through and burning through. And then once it reaches a point where there's no more fuel, that's when the crazy stuff happens. So if you're a low mass stars are fine, they're cutesy, they're demure, whatever. They die on a small scale and they'll just become, little white dwarfs, black dwarfs, that's cool. I care about the high mass stars. When the high mass stars die, they go from their red giant phases, which was the puff up phase that I didn't mention, and they go supernova, they go bang. Very dramatic, very diva. And once they do that, that's how we get the elements that they produce to enrich the interstellar medium. They're pushing all these materials away from it and just really kind of giving them all those ingredients. Then from there, if you remember, we saw the scale of the galaxy and the Whirlpool galaxy, how many giant molecular clouds were there. There's so many areas where this dying stars have the ability to be. And when you have all those together, they create these huge star formation driven winds, and they're called galactic outflows. They push this material up into the atmosphere, and that's how I get my elements. Okay, so we know how they're made. We know what an atmosphere is. How do we observe these cosmic ingredients? Because we can't, wait a second. I forgot I had another slide. I made these really earlier ago. Anyway, this is our periodic table of all of the elements, and it's showing the different processes of where they came from. So for this example, hydrogen at the top only comes from Big Bang fusion, but carbon actually has contributions from low dying mass stars, the cutesy demure ones, but also a little bit from the exploding massive stars. And this is really cool periodic table. This was put together by Jennifer Johnson in 2019. And I really, really like it because I've never really seen elements this way. But it also reminds us that, we're all making star stuff, which I think is kind of cute. And especially in times like these when we're kind of, having battles and politics and all sorts of things. Like I want to remind us that we're all intergalactic immigrants and we're all, connected in some type of way. So, just something to take home. So back to my point, because I forgot I had this slide. We can't just go shopping for our ingredients, right? We have to go look for them in another way. And the way we do that is really, really fun. And we use the Hubble Space Telescope to do so. We love her. She's pretty. She's, doing her best right now. But she's been up there for a really long time. But we love her. This is actually the observatory that I use. And specifically, I use the Cosmic Origin Spectrograph. It's just one of the several different instruments that are on here. Let me circle her. There she is. So she's on there on the Hubble Space Telescope. And if we look at her a little bit closer, you can see the two different detectors that are on here. You have the far ultraviolet detector and the near ultraviolet detector. So I work in the ultraviolet regime, and this is just looking at different parts of wavelengths. And what happens is the light comes through the detector, it hits on an optics, and then the images are diffracted, and then it comes to us on my little computer. And I don't know about you, but when I look at this, I see a fork. You'll see a little prongs? So, if I haven't convinced you the space is a soup and there's ingredients, there's a fork. I literally use a fork to do my research, but aside. So, using this telescope, we're going to do this an experiment called an absorption spectroscopy experiment. Because again, we can't just go grocery shopping for our cosmic ingredients. And the atmosphere that we're looking at is really, really diffuse. It's like our own. I was talking with my advisor today, and we've been talking about the interstellar medium a lot. And that's about, I think she said 100 cubic centimeters, atoms per cubic centimeter. That doesn't mean anything. It's whatever. But it's a lot denser than our actual atmosphere. What we're looking at, these circumgalactic mediums, it's 1 million times less dense than this. So you can't see it. It's just kind of almost like smoke, even less than smoke. So it's really, really hard to observe. So we got to use this measurement here, or this experiment, to try to see what we're looking at. So we have the Hubble Space Telescope, our Cosmic Origin Spectrograph, and we have our galaxy that we care about. And we specifically study galaxies that have what we call cosmic flashlights, or quasars. They're basically kind of a galaxy that's she's really, really active. There's so much light, so much activity that's happening in this galaxy. It's just a flashlight in space, essentially. That's all we're going to care about it. There's people that study quasars. I commend them. I don't, but I just use them as flashlights. And essentially, as the light passes from our quasar, it's going to pass through our atmosphere, come to our detector, and if there's any cosmic ingredients in there, it should take little bites out of our spectra, like Pac-Man. So if we look at this a little bit closer, I'm going to change our experiment. So it's up here. Here's our galaxy. light's passing through its atmosphere, coming to our detector, you get a spectra that looks like this. So here's we have flux, which is the amount of light coming towards your detector, versus wavelength, the UV spectrum that we're looking at. And the features that you see are all these little bites, and all those little absorption features are all different elements that are in our atmosphere. And what we specifically care about is our carbon. And if you zoom on it a little bit closer, this is a zoom in version of that. This is my profile fit to this absorption feature. And essentially this is all we're going to do. I look at lines all day and I take an integral. I take the area of this curve, and that's going to tell us how much atoms per centimeter squared is in our galaxy along our line of sight. So if you have a teacher or you told a teacher that integrals don't matter, they do. They matter very much to me. And this is all we're going to do. We're going to look at the amount of carbon, and I'm going to show you its different properties. Okay. So we finally made it. Enough background, Sam. That was too much talking. But what can carbon observations reveal about your galactic atmosphere? So I'll tell you a little bit about what I've been doing for this past 4 years. So when I was and a first-year grad, my first project was studying carbon content in relation to galaxies with different supermassive black holes. And the theory is that if you have a supermassive black hole at the center of your galaxy, it can impact your content in there. And you might be thinking, Sam, that's a really weird question. I thought black holes suck things in. You know, they're not going to explode anything out. What are you talking about? Yes, that is true. But those are more stellar mass black holes. So at the end of one of the star's lifetime, it can turn into a black hole. And the same kind of properties are for supermassive black holes, which are much, much, much bigger than stellar mass black holes. But they're also just slightly different. They're much, much bigger, and they can actually impart a ton of energy and also be a factor that's pushing material out, just like those star formation-driven winds do. But a lot is still not known about these black holes and what they do. So a lot of the information that we have about them has been driven by simulations. And simulations aren't always right, you know? They have different factors in them. I like to think of them as like different ways to make a chocolate chip cookie, okay? Some people call for 3 cups of chocolate chips. Some people want dark chocolate chips. Everyone's different. That's how it is with simulations. So some people in their simulations find that the more massive your black hole is, the more energy it's actually going to have to move this material out from the disk into the halo and actually past your halo outside of your atmosphere. So if we were looking at our observations of carbon, perhaps, you wouldn't see as much carbon in your atmosphere. It's just going to be completely blown out the bigger and bigger black hole massier it is. Other simulations are like, nah, that's wrong. The more massive your black hole is, the more energy it has to actually push this material into the halo, and that's where it's going to stay. So the larger black hole that you have, it's going to push it up there, and you're going to have more carbon observations. And so my job as a little observationalist was to just see what the difference is. Can I get data and figure out if which test is true? Do we have an evacuation of our atmosphere, or do we have an enrichment of our atmosphere? And so I was the lead observationalist for the COS-HOLE survey. This was an HST Cosmic Origins survey that was done in far ultraviolet. We looked at 8 different galaxies to see if we can get carbon observations and see if we could test this theory. The reason why we only have 8 observations is getting an accurate measurement of supermassive black hole masses is actually really, really hard. And thank God I didn't have to do it. I just looked at people's stuff that had these measured and started to build a catalog from there. But there's only about a couple hundred galaxies that have really, really well-determined supermassive black hole masses, so that decreased the amount that we could start with. Also, we have to do our absorption line spectroscopy experiment. We have to have this cosmic flashlight somewhere close to our galaxy that can light up our gas so that we can detect this carbon. So that also decreased how much we could have. And as a true scientist, we wanted to have some more constraints on there. We were constrained by stellar mass, so the mass of stars that you have in your galaxy. And all these galaxies had similar stellar masses to our Milky Way. So that's why you can kind of see some nice spiral ones in here. Some of them aren't as pretty as like having bunches of stars. They're a little bit dead, and we'll come to that in a second. But essentially, we have our small sample. I love her. She's great. And we start getting data and start looking at some stuff. So this plot here, we're looking at carbon. We have our amount of flux on the y-axis versus instead of wavelength, we're looking at velocity. And that's because I care about the kinematics of the gas. So we transform our wavelength into a velocity so that we're looking exactly at the galaxy. And the 0 velocity means it's right on the galaxy, and anywhere off is like it's moving towards you or moving away from you. And it's just important to know what the gas is doing, which is why we look at it in this form. And then, of course, I fitted some little curves to our lines. Again, I'm just going to take the area of this curve, and that's going to tell us how much carbon is in these atmospheres. And so now I get to do some science and plot against things. So here's our first plot. I know there's a lot. We're going to walk through it. I still don't get this all the time. Okay, so on our y-axis, we have our amount of carbon, those integrals that we took, versus our black hole mass. The size of the marker tells you how close this observation was taken to the atmosphere. So smaller markers mean it's much closer to the atmosphere. Like if this was the galaxy me, I take the observation here. The larger marker is further away. If it's colored in, like full, that means we got an actual detection. I had a nice little dip in our curve. Our carbon atom took some out. I was able to get a detection. If it's a hello, go back to where you were. If it's an open circle, that means that we didn't see any absorption. So it's just kind of like noise. So we just took an estimation of what's there. We call this an upper limit. We just really didn't find carbon, but we still we want to use the data we have. We do as best we can. And then the coloring tells us the rate at which stars are forming. So redder type ones are those redder galaxies, not really forming stars. Bluer means that they're much forming stars. Okay, so what do we see right away? Even with our small potatoes here, we can see that for galaxies with supermassive black hole masses that are less than 10 to the 7 solar masses, about right here, we have 100% detection fraction. We saw carbon. That was awesome. And anything that had a black hole mass greater than that, we didn't see as much carbon. We had a 33 detection fraction. I know, it's sad. We didn't have as much carbon. And you can be like, we figured it out. The higher massive black hole means there's not much carbon. We figured it out, right? No. Does anyone do statistics out there? Because I hate it, but yeah, we got one in the back. If anyone does statistics, you can't really make those types of things with 8 points. It's just not going to work. So we tentatively said, I don't think we're seeing anything with black hole mass here, but we'll keep looking. What we did see here is that galaxies that have a lower amount of carbon-4, so less than about 10 to the 13.5 atoms per centimeter squared, are not really star forming. They're all kind of red and gray. And anything greater than that are kind of blue. And that's a little interesting. We might look at that in a second. But I needed more data. So I went out and searched really, really hard. And now we can get to this plot. I ruined it. But I added 12 more points. Even that is a little bit small. But it's really, no one had done what I'd done. So there's not that much data. So we're looking at it now in a little bit different way. We're still having our amount of carbon on the y-axis versus our distance from the galaxy. That's with the size of the markers that we were just talking about. And now we're coloring it by black hole mass, where our lower mass black hole masses are in the pinky colors to purple, and then our higher massive black holes are in the blue color. And even with our more data, you might be like, Sam, I don't see anything on here. And you'd be right, there's nothing. This is my null result plot. Null results are still results. There's nothing going on in here. We do not see any kind of decline too much. We have a small linear regression, more statistics, but there's nothing really going on here. There's a really, really large scatter, and there's no trends with color. And so my advisor were like, okay, we added as much data as we could, and now we can definitively say, there's no significant trends between carbon-4 content and black hole mass. So my advisor were like, all right, let's rip up the game plan. Let's try something else. I also stole this animation movement from Tom. He inspired me to do that. Okay, so we got to look at it in a different way. What can we do? So on the y-axis, now we're looking at the rate at which stars are forming. On the x-axis, we have black hole mass. On the far right, we have black hole mass normalized by stellar mass. If this doesn't make sense, that's okay. They show the same things. We divided it by stellar mass because stellar mass is one of the ways that you can actually determine the mass of a black hole mass. And it's really, since getting these masses are really hard, it kind of introduces some bias. So we just trying to divide it up, but that's why we have that there. But what's really important here is the coloring. And this is what we call delta carbon 4. So I'm going to go back to our ripped up game plan for just 1 second. And so you remember this linear relation we had here? So basically what the carbon 4 coloring is going to try to do is normalize this huge scatter. So we subtracted the model of this line, these estimations, from our observations. So anything that's above this line is going to have a positive value, and anything below this line is going to have a negative value. So if I go back to our game plan over here, here's our equation, and that's essentially what we're seeing. Any positive values are going to be in the green to blue colors, negative values are going to be in the red colors. So excess, not enough. And what you start to see, which is really, really cool, is that they're about the same on both sides for black hole mass, but once you get to a black hole mass of about 10 to the 7, you see a branching happen. Does everyone see that fork? And this is really, really cool. We hadn't seen this before. where if at the same type of black hole masses, if you have a higher star formation rate, you have more carbon. And if you have about the same type of black hole mass, but a lower star formation rate, you don't see as much carbon, which is wild. We hadn't seen this before. And so if we rearrange the data so that our normalized amount of carbon, this delta carbon 4 value that we had, is on the x-axis versus our rate at which stars are forming, and now we're coloring by black hole mass, we have a really strong correlation. We're seeing something. This is really cool. And so we came to the conclusion that we have this tentative correlation between the rate at which stars are forming and their carbon-4 content in galactic atmospheres, which this was my first paper. It was really fun to move from having a null result to actually finding something. This was really cheering me up. I was very, very happy with this. Now, you might be like, Sam, that makes so much sense. Stars are forming in galaxies. The more stars are forming, the more elements you should have, the more carbon you should see. And I agree with you. I don't know why no one has looked at this before. And that's because we actually don't have much carbon observations. So this is a graph that my collaborator made that shows that carbon is rarely observed by other galaxies that have been done before, other surveys. So there's a couple on here, there's more out there, but we're looking at Milky Way-like type galaxies. This one called COS dwarfs, they were looking at dwarf galaxies, so galaxies much smaller than the Milky Way, and they had a lot of carbon, which good for them. But these other two surveys that were more representative galaxy surveys, they were looking at like Milky Way type galaxies, just kind of like understanding what's going on there in the universe, the galaxies that are similar to ours. They didn't have any carbon. And that's because if we remember back to our Hubble Space Telescope, there's these kind of instruments on there. It's really expensive, not like monetary wise, but like time wise, to observe these different ions. And so most people were observing oxygen instead of carbon, because they're like, we don't care about carbon. Oxygen's more interesting. I dare to disagree. Carbon's really cool. But that's why we didn't have any of these observations. And that all changed with the survey that I was a part of called the Civil Survey, which was trying to bridge the gap and actually get us those carbon observations so that we could test some new theories. And once I had my other survey, the COS survey, we were able to combine the data together and actually have a lot of carbon observations to test this theory and see if this tentative correlation that we found actually is true. And so this is some of the data from the survey that we got. We were doubling, almost tripling the amount of carbon data that we actually have in the literature now, which is really fun. Again, we're just looking at the amount of light that's coming in versus our velocity, and we have lots of absorption lines. So I can do lots of playful science. Okay, so here's one of the plots that we were able to make. We combined as much literature observations as we could. There was still a little bit of carbon out there before, but we combined COSLs, we have our new civil data, and now we're looking at that plot where we have the amount of carbon on the y-axis versus the rate at which stars are forming, and it's really pretty. We see that we have all these data points, so much better than 9 points. And what we do to start looking at this correlation is we're going to separate these two, all of our galaxies into two samples. We're going to have star forming and passive, and they're cut at this rate, which is 10 to the minus 11 per year. It's a weird rate, the rate at which stars are forming. But you can see we have a lot of observations in blue and not so much in red. And so when you look at the kind of statistics of this and do some covering fractions, you see that we get a 72% detection fraction for carbon in passive star-forming galaxies and only 23% for passive galaxies. And this was pointing to a significant dichotomy between these two. And we're really kind of highlighting this difference between star-forming and passive galaxies using the ion tracing carbon. This was not what I want to do. So this is my big result that I had for my second paper. What I'm currently working on, and I didn't include, and you can ask me about it later, is I also care about the gas that we're looking at, kind of looking at the temperatures and densities of this gas. But these are my two big results using carbon. And before I leave, as I have Megan talked about before, is I do a lot of outreach. I'm not just a research scientist. I actually care a lot about talking about science and telling it to the public. I'm trying to do that as a career. So if anyone wants to hire me, that'd be great. So when I'm not here, I do some other stuff. I have been a mentor for pre-map. So this is a program where we have undergraduates and we mentor them. They're their first years or transfer students, and we teach them research skills. David has worked on that. David can say hi. But essentially, we just tell them a little bit about how to do research, and then we give them a little bit of a project. So I've been a mentor to 5 students over the past couple years, and a lot of them have gone on to win competitive research internships. So I'm a proud mama bear. I also work with Raising East Team. Jake is also in Raising East Team. We go to a children's center for incarcerated students
in Snoqualmie, Washington, and we just work with them and kind of are like mentors. We do some experiments sometimes, which are the images that I'm showing here. I made the galaxy milk one. So I got to make galaxies for the kids. But it's really, really rewarding. I love working with them, working from day to day. And you're interested, if you want to be a volunteer, we're looking for volunteers. Anybody can join. It's really fulfilling, and I could sing praises about it all the time. Megan's also a member. It's really cool. And my last thing is that Tom, too, I forgot you do things. No, I'm just kidding. Tom was a 9 Sigma individual. He's basically a professor. But the last thing I want to talk about is the planetarium, which a lot of also the people that are here work on. And they just started their first Friday show. So if you've been interested in getting into the planetarium, you can start looking at their tickets. They're all free, but like you got to book a spot, and they go really fast. So I just wanted to talk to note that here. And before I go, I just have to say thank you to all of you. It's been a wonderful time here. I see people that are on this slide that are also here in person. It's been wonderful being with you for the past couple years, and I'm just so thankful to have had a wonderful audience and also get to serve you and serve the public of Seattle. So with that, I'm going to leave you with my key takeaways. What we found out is, supermassive black hole mass might not have a big impact on carbon, but star formation does, and star formation is really interesting, and so is carbon. It's a great tracer of atmospheres. And so I'm just going to leave this up. If you want to get connected, I'm going to be around for a while, and yeah, I'm happy to take questions. Yeah, in the back. Yeah, the question is, how do galaxies mergers impact things? And they're a big component. So my collaborator, Dr. Nicole Sanchez, she also used to run AOT. She's on the simulation side of looking at the circumgalactic medium or galactic atmospheres, and mergers are really, really important. So she studied genetically modified galaxies in this survey, basically, that we're smashing together and how that impacts it. And it's this kind of merging of gas and also kinematics. And as they swirl together, that has tons and tons of implications. And I do not remember all the different points about it, but there are people that are studying them, and that's a good question I should look up before I do my test on Friday. But they are important. I wowed you with my excellence. Yeah, Liam. Why is carbon better than oxygen? A good question. So the physics of carbon is interesting. So ionized carbon is what I typically use carbon for. I didn't mention that because I didn't want to go into physics, but essentially the carbon that I study has lost 3 of its electrons. So either through a photon coming in and knocking it off, it's lost some electrons, or 2 different ions colliding with each other. And the same can be said for oxygen. The ion that I use is oxygen 6. Which has also lost multiple electrons, so that also 3 electrons. But because of the physics, they have different ionization potential energies. It just means the amount of energy it takes to get to this higher state of being. It's not neutral, it's excited. And why it's interesting is because they kind of live in different gas phases. So the galactic atmospheres, again, are not just kind of these fluffy, non-moving places. They're really, really complex. That means it has different temperatures of gas and different phases. So you can have densities that are really, really thick and clumpy to multiple cloudlets to some that are not. And Liam knows this. Liam works on CTM. But they're kind of in these different regimes. And so what was interesting about finding these things about carbon is that it's acting much, much like a higher ion than its oxygen 6. And a lot of the times it's compared to lower ions, so like silicon 3, carbon 3, things like that. So my research that I didn't show to you here, we could if we wanted to. Hold up. Is it over here? Did I have it in the backup? Ah, here we go. So I actually was looking at these density and temperature regimes. So we have temperature on here, nitrogen, or not nitrogen, density here, and we're comparing the different ratios between carbon and oxygen. And when you put them together, you can start seeing some really, really fun stuff. And I don't think carbon is better than oxygen. I like to put them together. I like to think of them as friends. But they can start telling us some really, really cool things as well about them. Oh, right here? Yeah, so the question is, when I got my more carbon, could I go back and look at the supermassive black holes? I could. I did not. I was thinking about it as an undergrad project, actually. So what you could do is you could kind of measure the black hole masses of the galaxies that we're looking at, but they wouldn't be as dynamically measured, so they wouldn't be really super, super accurate. So which is why I didn't do it in the first place, because I wanted to have that super accurate measurement. But what I did find by going to a conference recently is that a lot of people are getting more accurate measurements of these black holes in galaxies, and so I could work with a student, maybe do an HST proposal, and look for these galaxies that already have measurements, see if there's that cosmic flashlight around it, and do some more. Which is, I want to, but I also would love to do other things in research. But if there's a student that wants to, I will teach them how to do it. But we can start doing it again. Any last questions before we give it over to Dr. Tom Wagg? Well, after we do trivia, so in some type of order. Okay, I think I'm back.
All right. I know we just clapped, but I want to give it up for Sam again. I feel like it maybe goes lost, like how much Sam has actually done for AOT. It's an incredible amount. Every single social media post you've seen in the last 3 years has been Sam. I'm guessing she's probably the reason you're even here tonight. So I think, I really appreciate her, and I'm going to cry when she gives her defense. I'm really soft inside. Anyways. Okay, so now we're going to move on to trivia answers. I can't get this to stay up. That's better. Okay, trivia answers. So we have one super duper winner that got 10 right, and 4 kind of winners that got 9 right. But if you're not first, you're last. Just kidding. You'll still get prizes if you got 9 right. Now let's go through the trivia answers before I announce winners. Okay, number 1, spiral galaxy. That's the whirlpool galaxy. Sam said it. Dust obscures star formation from our view. It also teaches us about star formation, as we've learned tonight. The inner arms, apparently, are the hardest to study. It's all hard. You know what? Sometimes things in life aren't fair, okay? That's the lesson we're learning tonight. Okay, number 4. The CGM is the diffuse gas surrounding a galaxy. Feedback from supernova and active galactic nuclei are most responsible for regulating star formation. 2 stars orbiting each other are a binary star system. Eclipsing binaries are the most useful for determining stellar masses. Right, Tom? So true. Circle or ellipse is how binary systems move around each other. Type 1a supernova can occur if white dwarfs merge, and as it turns out, British people like to say I'm on it like a car bonnet. Tom actually says that so frequently, I need you to understand. Okay, but with that, let me announce the winners. Now, before I announce the winners, the astronomy students would not have submitted any answer sheets, would they have? Okay, I believe you. It was some of the team names made me suspicious. Okay, so the first winner, the overall winner that got 10 right is Black Hole Sun. Nice! Okay. Oh, and as a reminder, if you got a prize, just wait till the end of the second talk and come get it. Okay. Next winner is Bears. Bears? Any? Okay, next winner is Denby, or Derby. Denby? Okay. Nice. And then the next winner is Onions Julienne. Who's that? Oh, nice. Oh, yeah. Okay, and then finally, the last winner is AB, but not Astrobio.
I wasn't even there.
Okay, I feel like arbitrage. This person is Sam's partner. They say they're claiming that she did not help him. I don't know, guys. Show of hands, do we believe them? Okay.
Fine, you can have a prize then. Very well. Okay, so with that, we're gonna go on like maybe a 5 to 10 minute break, so you guys can order cycle dogs if you want, or you can go in and get another drink from the brewery, and we'll be back in like 5 to 10 minutes with the last talk.
starts a PhD, does some research, and then finishes the PhD. Just all in a very simple, straight line. It doesn't work like that. It looks a little bit more like this, where it's a little bit more of a meandering path. Where I started up here, and I started doing some gravitational wave stuff, which you may remember I talked about a couple of years ago if you were here. I thought that was fun, but then I got working with someone here on the solar system and thinking about near-Earth objects, trying to protect us from collisions and that sort of stuff. Did that for about a year. Didn't work out for a variety of reasons. You know. After that, I was like, okay, I'll try the exoplanet thing again that I did when I was 15. And I started thinking about radio measurements, trying to better understand how we characterize planets. And I tried being an observer, and I just couldn't do it. I'm sorry. I like to live in my make-believe theory land. And at this point on my little journey, it's like, you know what? I really miss stars. Stars are fun. You know, like, asteroids are just rocks. They don't do much. Planets, not much more than that. Stars fun. And so at this point, I spoke to my, committee that you have of like 3 professors and said, this is what I want to do. I want to do stars. And they were like, well, there's no one here who's really got expertise in that. Do you really want to do that enough? It's a good idea. And I was like, look, guys, I really want to do stars. And they didn't believe me, and I kept pushing. And eventually, I came up with a solution, which was that I wrote a thesis proposal, where you're supposed to write a thesis proposal. And then what I did was write this 10-page thing being like, look, guys, this is compelling as a research problem. And it is feasible logistically. And I outlined exactly how it would work. And at this point, I think they just lost their patience with me and were like, fine, do it. And, it worked out. So I've then since then been doing some stuff about astroseismology, which is about the pulsations of stars. Now that can tell you about their insides. And most recently, which is the stuff I'm going to be talking about today, is how you can combine binary stellar evolution and galactic dynamics to consider stellar kinematics and better understand things through these ways. So we'll talk about that. But what this means is that my thesis kind of combines a bunch of different random topics, which have culminated in a bunch of different random papers, where I have done some work thinking about gravitational waves and whether we can use this new space-based gravitational wave detector. There's a ground-based one called LIGO, which is just in central Washington. You should go visit. I've done some stuff about NIM and trying to predict where they'll be and how many we'll see. Software citations, boring, don't need to talk about that. There's some astroseismology, which I've skipped over today because I don't want to keep you here forever, but that's about how stars pulsate and how that tells you about what's going on inside. We'll skip that. And then I'm going to talk about these 2 things here. This is really what we're going to be focusing on. It's the most recent 2 papers, which is my friend Cogsworth, which is a thing I made, and then kind of applying it to thinking about where we end up with all of our supernovae and how that might change feedback, which Sam has wonderfully already explained a lot of that. So, what our journey is going to look like today is essentially a 4-step process. First, we're going to be thinking about introducing ourselves to massive binary stars and seeing their wide-ranging impacts across all of astrophysics. Stars are the best. We're going to think about what we can learn from positions in kinematics and why Cogsworth is a perfect tool to do this. I don't really need to sell it to you guys, I suppose, but I did in my defense. And then I need to think, how can those binary interactions between 2 stars delay and displace supernovae, and what does that mean for a galaxy? And at the end, we'll just talk about, future outlook for the research. So, first things first, introduction. Let's think about these massive stars and why they are so fascinating. For these purposes, massive stars, at least the way I call them, it's about 7 or 8 times the mass of the sun. It's basically the ones that explode. We're looking at supernovae. And so, if you take a single massive star, one that just lives its life all alone, then it goes through its life, it reaches the end of it, it explodes in a supernova, and it results in a neutron star. In this case, let's say this one was like 9 times the mass of the sun. But if I start putting it with a companion, in this case, it's in a binary system, the way that it interacts with this star is going to change the final outcome of this star just by putting it with another thing. And that can change if maybe I make the other star a bit larger, or if instead I put it a bit closer. All of this can change the outcome. What you can have is the same system could become an X-ray binary. This is a system where you've got a compact object, let's say a neutron star that was usually going to form, and then another star nearby that pours material onto it. And this accretion basically releases these jets of X-rays that are really bright. You could get that. Alternatively, you could have a runaway star. This is Zeta Ophiuchi. You can go and see it in the night sky. And this is a runaway star. This is a star that has been in a binary. One of the two stars has exploded, and the other one is now flying across the galaxy at hundreds of kilometers per second. You can kind of see that here, where the star is moving so fast that it's ramming into the gas and heating it up. So this is this kind of ram pressure that you're seeing light up the gas. And if you're really lucky, you could get yourself a gravitational wave source. So in this case, both things explode. You end up with like two neutron stars or a neutron star and a black hole, and they eventually spiral in together, merge, and shake the fabric of space-time. So you can see massive stars are quite fascinating. But the nice thing is they're also ubiquitous. They are everywhere. The vast majority of massive stars that you see out there are formed in binary systems or even triple systems or more. So here's your first plot. This is from a paper by Stella Offner. And what this is showing you is as you increase, the plot isn't there yet, don't worry, you're not seeing it. This is showing you it's going to be low mass things here, high mass things here, and how the multiplicity changes. It looks like this. I want you to focus on these bold ones here. Now what you're seeing is that for something that's about the mass of the sun, around 1, about 50% of things are in binaries. We actually got sort of lucky that the sun is just by itself. You can also see that once you get up to your, O stars, things that are more than, 15 times the mass of the sun, they're all in binaries. These things are everywhere. So binary stars are important. And they're not just binaries, they're interacting binaries. These things are so close that they're really talking to each other. Over 70% of O stars will exchange mass with their companion at some point in their lifetime. It looks something like this, where they kind of pour material from one onto the other. What does that do? Well, you can end up with, only 30% of them are effectively single, where they're wide, but you can have some sort of stripping. The outer envelope of the star can be pulled off. You can have accretion, where you gain material from a companion, or spin up, where you make it spin faster. And even in, nearly a quarter of cases, the two stars can merge together and really change the way that they evolve. Now, these massive stars, they're fascinating, they're ubiquitous, and they're also impactful. This is a lot of what Sam has been talking about, is that these stellar winds and supernovae are providing this critical feedback for galaxy formation. They're reheating the gas, preventing future star formation, changing the way the galaxy evolves. And if you want to look at what the galaxy actually looks like, compare it to your simulations, you have to include this feedback in your simulations, or it doesn't look anything like anything real. And they also are driving a lot of the transient things that you see, all of the kind of supernovae, all of your short gamma ray bursts, and all of your progenitors for the gravitational wave signals that we've seen. So they're very, very important. They're fascinating. They're ubiquitous. But perhaps most important to me, they're uncertain. There's still a lot that we don't know about binary stars. A lot of the parameters that control their evolution are unconstrained over several orders of magnitude. Could be 0.1, could be 100, I don't know. For example, this is a common envelope. Two stars have got so close to one another that they've been pouring material so that the cores of the two stars are now orbiting within a common large envelope. Now this parameter, alpha, will tell you how easy is it to unbind that envelope. How easy is it to throw it off into the galaxy. And this parameter, we don't know this over like a factor of 100. We also don't know about supernova natal kicks. This is when a supernova goes off, not all of the material is spherically symmetric. Some of it will go slightly more in one direction or the other. So you all know Newton's third law. We've got something pushing you that way, you're going to get kicked this way. You're going to end up with a supernova natal kick. Now we don't know quite how strong those should be, how they should be distributed. Are they bimodal? Not quite sure. It'd be great if we could learn a bit more about that. Well, that's what the thesis was about. So what I've done is kind of a few different theoretical things thinking about modeling of binary stars. And first things first, I want to think about positions and kinematics. But even before we get there, and before I forget that there's a title slide in between, before we get there, we need to think about something called binary population synthesis. So this is a way of synthesizing a population of binaries. But it approximates stellar evolution. It's basically you can, if you want, take a coupled set of differential equations and properly solve them and evolve your stars forward. Or you could do that a bunch of times, get a bunch of stars, and then basically just fit lines through it and say, okay, it should evolve like this. This is how the mass should change. This is how the radius should change. And so instead of having to do your whole complicated simulation, you basically just plug in equations into a line and you can see how they move. So what you get from doing that is an approximation of stellar evolution that kind of looks like this, where I'm sure you haven't spent tons of time looking at Hertzsprung-Russell diagrams, but, bit of fun on a Wednesday night, right? So what this is showing you is the luminosity and temperature of the star, but point is, you can kind of see it evolving along, and you can trust me that the different colors are different stages of stellar evolution, where you've got things that are burning hydrogen or things that are burning helium. And you can see in some cases, if you're looking at those orange lines, they look like very straight lines, right? These are approximations. They're not actually that straight in reality. But it does a pretty damn good job of getting it close. And on a population level, it approximates it very well. And what this allows you to do is have very detailed, parameterized prescriptions for your physics. You have that alpha common envelope. You have the supernova natal kick that you can change. And the important thing is, because it's approximate, you get to rapidly evolve large populations. And this is what I spend a lot of time doing, is changing all of those parameters and seeing how on a population level things change. And so the way that you use this is first you decide some initial conditions. You say binaries should be formed, with approximately these masses, these separations between the two stars. And then you evolve them, and you select out a subpopulation that you care about. It could be those X-ray binaries that we talked about. And then you measure the properties that they have, the masses, the orbital period of how long it takes the two stars to orbit one another, maybe their eccentricity. And then you compare it to the actual observed things. And so based on all of your simulations, with all of your different variations, you can start to say which of these parameters most recreates the observations that we see. Now, within these three, there's kind of one that's an odd one out, which is the runaway star. Because I would argue that the mass of this star is not the most interesting thing about it. The most interesting thing is this thing is flying across the galaxy at hundreds of kilometers every single second. It's its extrinsic property, not its intrinsic property that you care about, the rate that it's moving. So arguably, the thing that I've kind of been trying to push for people to do with my thesis is that you can constrain binary physics using positions and kinematics of stars. If you have a single massive star, then it will stay close to its birth site. It's going to live fast, it's going to die young, and it's going to die close to where it's born. For a binary star, it's not quite the same. They can start acquiring some very high velocities. You can have a situation where you've got two stars here. The more massive star always evolves more quickly. So in this case, that more massive star is going to evolve, going to reach the end of its life, explode in a dramatic supernova, and leave behind a black hole. And now that black hole is going to fly off with that natal kick that we talked about because of the asymmetry in the explosion. And as it flies away, it's going to unbind the binary. And so as a result, the other star is going to fly away with whatever its pre-supernova orbital velocity was. And so this thing is flying across the galaxy, carrying information about the binary that it was in beforehand. And so if we observe stars and remnants at large separations with reduced spatial correlations, which we do, then all we need is someone who can possibly give us the theoretical modeling framework in order to reproduce this. Who could it be? It's me. It's also someone called Cogsworth. For reference, this is not an acronym. I just thought it was fun to say. And so this combines two different things. First, Katie Brevik's population synthesis, which we talked about, population synthesis code called COSMIC. And what it does is it puts it together with GALA, which is a galactic dynamics code. And what that means is that you can move things through the galaxy. So for an example, if we look at the galactic orbit of a binary that disrupts, one that breaks into two, I'm going to show you, this is the same kind of picture from three different angles. One is kind of looking face on at the galaxy, and then side on, and a different side on view. And here's how it evolves through the galaxy. So it starts off at that black point, goes along, and then supernova goes off, supernova goes off. And after the first one, you can see that the blue line emerges. This is the binary disrupts, and the two stars go in different directions. And they start to kind of move across, and you can see, let's let it play one more time, the supernova here and here. 1, 2. And so I can tell you that these are like hundreds of kilometers per second kicks that these things are getting, which disrupts the binary. And this is just looking at the first 130 million years. These stars are still very young, or black holes rather. If we look at them over 2 billion years, then it starts to look even more pretty. You can see them going around the galaxy, ending up in completely different parts of the Milky Way, despite the fact that they formed right next to each other. I really like this one because, yes, you get this beautiful rosette, but you can also see in between, there's a star hidden in the center. You see it? Cute, right? Yeah, it's all a simulation. Anyway, it actually is. So, that's kind of the core of Cogsworth. What can you change? Well, it's very flexible. You can change all those binary physics, all the alpha, the supernova natal kick that we want to kind of flip around and see how things change. We can change that. We can change your initial binaries. How big are they? How massive are they? How close together are they? That sort of thing. We can change the star formation history. Where do you form your stars? When do you form your stars? That could change how we observe things. What's the galactic potential? I'm talking gravitational potential of a galaxy. Are we thinking about a Milky Way? Are we thinking about a little dwarf galaxy? Who knows? We can do them all. And then there's these things called Fire and Chunga, which do hydrodynamical simulations, which are the simulations that Sam was talking about. These are things that include all of the gas physics, all of the detailed galaxy evolution. And these are nice because I can just take those simulations, and I've set Cogsworth up so that all these things can feed directly into the dynamics, so you can just post-process them. So what this means is that you can take their initial spatial correlations, which are great because stars don't form by themselves. They form in clusters, so they have initial spatial correlations. They're usually more close to one another. And you know, if we're going to get the final positions and velocities, we want to get the initial ones correct. So what this means is that, here's another plot. What we're looking at here is galactocentric radius, galactocentric height. So I'm basically just looking at position within the galaxy. And I'm going to start the cluster off here and evolve it upwards that way. Looks like this. So, in the background, I agree with Sam, are the grey stars, the boring stars. These are the low mass stars. They don't explode. They just kind of mosey along. But they do disperse over time. You can see the galaxy has some initial velocity dispersion, and so they kind of spread out over time. But the interesting ones are the massive stars. We're, of course, all fans of massive stars here, particularly massive binary stars. You can see, for example, this blue one here. We have one supernova, we have two supernovae, where all these dots are, and then it gets ejected from the cluster. But it stays as one binary. It's just one line. Cogsworth also, you can see, this purple one, this one, it forms a neutron star here. Supernova kicks it this way, but then the other star goes this way, and then eventually goes supernova and gets kicked up this way. Two things end up in completely different directions within the galaxy. And you can even see, if you get really lucky, if you're a star, and you're this green one, you goes along, you get a late supernova that's weak enough that you don't even disperse from the cluster. You get to stay with all of your friends for the next billions of years. And so Cogsworth does all that simulation, and it does all of them at once, and it can evolve millions of binaries at any given time. And what that gives you is rates and distributions of your intrinsic population, that usual stuff that we were talking about, and what it's added to it is all of the kinematics, all of the positions and velocities of your massive stars and compact objects. So what this allows you to do is, for example, prove that positions are sensitive to binary physics, and as Sam says, my research does have value. So this is a side-on view of the galaxy. We're looking at it in X and Z, not Z. And I'm going to show you this in 4 different ways. It's the same binary population that's been evolved in 4 different ways. The top half is focusing on the Milky Way, and the bottom half is the Carina dwarf galaxy. And then from left to right, I'm taking a regular common envelope, that thing I was talking about where the 2 stars have unstable mass transfer. And on the right, what I'm doing is I'm making it less efficient. And I'll tell you what that means. And these are the positions of all of the massive stars at present day. And so, you can see this one's much bigger. It's a Milky Way rather than a dwarf, so it's smaller. But what I'm demonstrating is that in these 2 galaxies, even despite the fact there's all sorts of different galactic things going on, if I change the binary physics, then suddenly the positions of my stars, they're all a lot more squished down. The galaxy looks thinner. And this is because if I make this less efficient, I have more situations where it's not able to eject that envelope. And so the 2 stars merge. So you get fewer situations where you've got 2 stars, one of them explodes, and then the other one goes flying. So that's how you get things that are like all the way up here. So this is just a demonstration that positions do hold information about the binary physics, and that my research has value. And so overall, last thing, given all those things, that's just like what's actually out there. But what we want to compare against is what do we see? And that is the observable properties of our intrinsic population. And so, long story short, we use this thing called MIST, which tells you it's bright in this filter compared to what it is bolometrically. Combine that with dust maps, because we know that dust gets in the way of our stars, and so we want to see quite how faint this thing would be. And then, depending on different telescopes, so we're sensitive to different regions of the galaxy, so you get these selection functions. And what that means is that you can then now just take one function from Cogsworth and make this color magnitude diagram similar to that Hertzsprung-Russell diagram. That point is, this is where all your main sequence stars are, this is where your white dwarfs are, this is where your more evolved stars are, and you can compare that directly to observations. So, what can you do with this thing? Well, don't ask me, ask all of the lovely people that I work with. First, this is Simon, Vita, and Reed. They are undergrads, and they have been thinking about the offset of short gamma ray bursts from their host galaxies. These are released when 2 neutron stars collide and merge as a result of gravitational wave emission. And as they do that, they send out this huge burst of gamma rays, and what we have seen is that they are observed to be offset from their host galaxies. They're either not found directly in the center, or they're found slightly offset, or they're like completely out there without any galaxy at all. And so what Cogsworth can do is evolve a huge population, find all the binary neutron stars, find exactly where they are relative to their galaxy, and model this exact effect, and compare to the lovely observations that have been made. That's one thing you could do. You might also care about LISA, which is the Laser Interferometer Space Antenna, planned future space-based gravitational wave detector. What Frank is thinking about is, could we better identify double white dwarfs? System where you've got two white dwarfs spinning around one another, because you can't really tell if those are there or if it's maybe something more massive, two black holes, a black hole and a neutron star, just based on the mass. And the idea here is, well, maybe you could use something beyond the mass. Maybe you could use the location, because these are things that have got a kick. They've moved around. And so they won't necessarily be found in the disk of the galaxy. They'll be found higher up. And so what we can do is simulate it using Cogsworth and something called legwork, which is a different code I used back when I thought acronyms were cool. Youth. And so that's one other thing you can do. And lastly, this is a pre-map project, what Sam was talking about, where Hannah and Cavan were thinking about the galactic underworld, which is just a fancy way of saying, where do you find all of the black holes and the neutron stars in the Milky Way? And this was simulated by a reasonably recent paper, but they did something which, of course, I'm not going to be a fan of. They assumed all of their stars are single stars, despite the fact that I have just shown you a plot showing that actually all of the massive stars, which are the ones that form the black holes and neutron stars, are all binary stars. And so basically we're trying to redo this and thinking, how do binary interactions change this distribution, and how could this kind of influence this galactic underworld, as this paper called it? So that is kind of the in-between part of this is what Cogsworth is. It's something that lets you simulate kinematics. You can have a variety of applications, and you might be able to use it to constrain binary evolution if you have lots of observations of positions and kinematics. So that now takes us to an actual application of it, something a bit more detailed, and thinking about the impact of binary interactions on the location of core collapsed supernovae. This is just basically your regular supernova. And how does it change the feedback in the galaxy, the stuff that Sam cares about? So, one question you can ask is, how long after you form stars can you have a supernova? What's the kind of maximum time you could have? If you ask a single star person, they'll tell you about 44 million years, give or take, depending on the kind of age of the system. But I can tell you that you can actually get them happening up to 200 million years, just through binary interactions. You might also wonder how far a progenitor could travel from its parent cluster. How far away could it get from a star-forming region? And they'll tell you it's maybe 100 parsecs, not very far. I'm going to tell you you can get them up to 3,000 parsecs away just from binary interactions. So let's show you why. And first, let's show you why you should care. So we talked about how feedback is an important thing for a galaxy. If you have a bunch of stars that form in this dense natal cloud of molecular gas, and you have this star that's just a single star, it's all alone, and it just dies right there, then that has a supernova. That's going to heat up the gas. It's going to prevent future star formation. And it's going to enrich the regime. But what about this star? Now, this star's a little more popular. It's in a binary. But, you know, things go wrong. The binary breaks up, and it gets disrupted. And so as a result, it gets ejected, runs away from its problems. And over on this far side of the galaxy, it finally reaches the end of its life and explodes. So what does this mean? Now we've got less feedback happening in our dense region, so maybe that's going to allow more star formation to occur. And we also have a supernova going off out in the middle of nowhere, which is going to end up with enrichment and excellent new star formation, which could be very interesting. So how often does this situation actually occur? That's kind of the goal of this project. And the thing that you should keep in mind in all of those simulations where, you know, Sam was talking about the different ones where different black holes do different things, well, all of those simulations, regardless, are all assuming that all of those stars are formed as single stars without a companion. And, you know, I'm about to show you why that's a problem, because if you look at their core collapse supernova feedback rate, it's a two-step function. It is literally this plot. This is not a cartoon. This is actually what they do. It's just like, yeah, it's about this, and then it's about this. And importantly, it stops at about 40 million years, despite the fact that other people before me, this guy, have shown that you can extend this. And I am also going to demonstrate that you can get them happening really far away, despite the fact they assume they all happen right there. So how could that change your galaxy? Well, we did a big simulation, many big simulations when many went wrong, based on this fire galaxy. It's just a label. And what we did is take every star particle. Now I say star particle because these simulations, you can't evolve an entire galaxy of binaries with gas. So what you do is you're like, okay, here's a particle that represents 10,000 solar masses. Simpler way of doing it. I took every one that formed in the last 150 million years, and I turned them into actual stars. So because I'm not doing the gas, I can evolve them all. So I draw a population, I get 2.5 million binaries in my galaxy, and I evolve them forwards until present day through the galactic gravitational potential or the distribution of mass that's based off that galaxy. And this is what we see. So I'm going to show you a plot that has a face-on and an edge-on view of the galaxy. Looks like this. Isn't it pretty? We've got some nice spiral arms. We've got some random star formation. We've seen it. It looks like a disk from the side, right? And we have regions where there isn't even any recent star formation. It's basically holes in the galaxy. I've tricked you. This is what the single star population looks like. What happens if you add all of my lovely binary stars? It starts to look a little bit more messy. It's going to flip back and forth. So what you can see is things really reaching the outskirts of the galaxy, really giving it a lot more spatial extent. And you can also see it's starting to fill in those regions where there was no star formation. Now you're actually having things explode there. And that's going to really change the way that the galaxy evolves. So let's be a bit more quantitative, if that's a word, and think about the supernova timing. I'm going to show you a histogram in a moment, and it's going to show you the time since cluster birth. This is 0, this is 200, this is 44, where they think it stops. And I'm going to show you the rate of all of your supernovae as a stacked histogram with some different colors. If you see dark blue, those are your primary stars, your initially more massive stars. Secondaries are the kind of younger sibling. This is your initially less massive star in the binary. Those are going to be green. Light blue, not many of these, don't worry about it, but they're effectively single stars. They're so wide that they don't interact. Now this is purple. This is important, pay attention. These are merger products. These are systems where you've had two stars that have evolved along separately, then merged, then exploded. So it's a merger before the explosion. So, what do we see? Okay, it looks like this. So, these dotted lines are showing you what regular simulation people will assume. And you can see that they assume it stops at this point, despite the fact that I have this there's like a huge tail to the distribution. I will tell you, so that you don't have to integrate it by eye, despite how important Sam says integrals are. That's about a quarter of the population happening later on. You can see that for the blues and the greens, it actually does a pretty good job with those dotted lines. That is about where they end. There's a couple happening later. That's because of binary interactions. But the important thing to talk about here are the purple ones, our merger products. How on earth am I getting a star to explode after 100 million years, when by any rights they should have died long before that? Well, let's say you have two stars. Each of them are 6 times the mass of the sun. Neither of those stars is going to explode by themselves. They're not massive enough. They'll just be boring and they'll become white dwarfs. But you put them close together. Then they will evolve slowly because they are lower mass stars. So it'll take a long time for it to happen. And then they will evolve, merge, become a more massive star, and then they can explode. And now what that gives you is a supernova at 100 or even 200 million years after star formation ends. So you can start to get this real long smearing out of the feedback in the galaxy. So that's time. What about distance? I'm now showing you the location of the supernovae, or I'm about to show you rather. You can see this is the distance from the parent cluster in parsecs, and it's on a log scale now. Isn't that fun? So again, stacked histogram. Important thing to kind of keep your eye on, this 10 to the 2, 100 parsecs. That's kind of your important line. Things to the left of that, who cares? It might as well be 0. Things to the right, it starts to matter. So what you can see is that your blue and rather, not the green ones, those are going to be important. Your blue ones don't really go any further than 100. They pretty much cut off at that point. Primary stars, they're pretty much like single stars. Doesn't really matter. It makes sense that it doesn't change much. Purple ones, these are merger products. I've just shown you that these can live for a lot longer. So if they live longer, they have longer to disperse. You remember those gray lines from that plot that was kind of spreading out over time? The purple ones just have more time in that, so they spread out further. They get slightly further. You can see there are some that exist beyond 100 parsecs. And then the green ones, these are the fun ones. These are your secondary stars. In this situation where you've had a primary explode, secondary flies off across the galaxy up to several kiloparsecs away. Bear in mind, we're like 8 kiloparsecs from the galactic center. This is a long way. And then explodes. So we're getting things happening far away. So let's look at this in 2D. What we're seeing here is the time. Here is the distance. So it's kind of these two plots combined. And this is the difference between single stars and binary stars. So the blue is what everyone assumes these days. It's a density distribution. It cuts off at about 40 million years. and they don't go much further than 100 parsecs. But in the background are the gray binary stars. You can start to see these look very different. Importantly, there is more feedback because you get low mass stars exploding in mergers. So there's about 11% more supernovae than have previously been accounted for. There's late feedback. You can see we have this long tail that exists 2 long times because of mergers. And there is displaced feedback that is going like very far within the galaxy. So this looks like it's something that's important. But one thing you should do as a simulator like me is that your theories are not necessarily correct. You need to check, based on all of these uncertainties, how do your results change? And so we're going to go through this table in great detail. I'm kidding, no, we're not. And so the main distribution I'm going to show you is robust across variations. First things first, here is the fiducial model. Think of it as your default model. I'm going to show you how the distance changes as I change some physics. And what you can see, the different colors are the different subpopulations, and the gray is the total. And what I'm showing you is the interquartile range. It's basically just where the majority of the distribution is found. And the thick lines, particularly that dark black line, is the median. This is just like the average of your distribution. And I'm going to show you this for a bunch of different things. I'm going to show you for common envelope physics, mass transfer, when the 2 stars exchange mass, supernova natal kicks. How does this change these things with these specific variations that we won't get into? Well, it looks like this. I want you to focus on the black lines in the background. You can see these don't really change much. This is like a couple, parsecs. It's basically nothing. The distance distribution here is robust to these variations. So yes, I don't know what this alpha value is. I don't know what this beta value is. No one does right now. We haven't constrained it. But it doesn't matter. It's actually really nice. These simulations, yes, it's uncertain, but because one population decreases, the other population increases, it actually ends up not really mattering. You can see that in the green ones, this green bar looks very different from this green bar, right? The secondary stars have a bit more sensitivity to this, but the main distribution is robust. I also have one more here for you. Don't worry about the details. Point is that as I decrease metallicity, which is basically saying decrease the metal content of the stars, which is like earlier generations, so long into the history of galaxies, what you see is an increase in both the distance and the time. So the time sort of makes sense because if you go to lower metallicity, lower mass stars can explode. Those evolve slower, extends your time. Distance is a little trickier. I spent several days trying to work this out. But this is basically a lower metallicity, those earlier generations of stars. Your stars are a lot smaller. And so what that means is they can get closer together. As your stars are closer together, they're going to spin around each other faster and faster. And so when they do disrupt, they're going to end up going a lot further. So you end up with extended distance distributions. This is going to be important in a moment, I promise. So what does this all mean? I've just given you a bunch of plots and a bunch of data. What does this change in the way a galaxy evolves? Well, it depends who you ask what it's going to do. But the important thing is that it impacts the star formation rate. The rate at which stars are formed over time in the galaxy has changed, and it changes how much energy is injected back into the galaxy. Importantly, if you get supernovae in low density environments, remember those kind of the gaps in those spiral arms. If we get supernovae going on there, which I'm showing that you do, that can start to dictate your galactic outflow rates, or as Sam would say, good, it is changing the ways in which the galaxy evolves, and it's probably changing that galactic fountain that we've all seen that kind of impacts the CGM. Look at me connecting talks. And these effects are more pronounced at high redshift. In astronomy, when I say high redshift, I basically mean further away, early universe. And at early universe, we have nice pictures from JWST of these galaxies. They're a lot smaller. Galaxies are a lot smaller. And what I've just shown you is that feedback is both more delayed and more spatially dispersed at high redshift. And so what this means is that instead of happening in a little bit of the galaxy's small and the supernovae are going further. It's going to basically happen all over the galaxy at once, which is really going to change the way galaxies evolve. So for people caring about early universe stuff, this research is going to be particularly useful. And so takeaways from this section are basically just, there's a lot of feedback going on. Binaries are going to delay and displace it. These results are actually pretty robust to uncertainties in binary physics. And I didn't talk about it, but there is a new model that I've made that can go straight back into those simulations for people to use. So last thing, and this bit's super quick, is just where do we go from here? First things first, I want to try and get away from my make-believe theory land and actually do some proper observations. Well, not do the observations, that would be a hassle, but I'm going to use other people's observations. So there's like a wealth of observational data sets out there. In particular, if you look at nearby galaxies, they have these beautiful maps where you can see contour lines and this nice background map of where all the gas is. H1 and H2 regions of star-forming gas. And then all of those little dots are different colors, are different types of stars or supernova remnants. So you can see, well, I won't make you squint, but you can trust me that some of the colors are more correlated with these regions than others in a way that I would expect from my simulations. And now I can properly do the simulations and do a proper comparison of these spatial correlations. So that might tell us, based on which of my simulations match best, which of the binary physics is most likely to be correct. Or more likely, I'll just rule out some. The other thing I want to do is think about Gaia and runaway stars. This is a space observatory that does astrometry to get very precise positions of stars and also their velocities. I care about runaway stars. These are the things that are moving really fast. And in, sometime next year, hopefully, Gaia DR4 is going to come out with 1 million new binaries, which I am going to be delighted about. Because what this means is I can identify runaway stars from this, compare them to my Cogsworth simulations, and start to better understand mass transfer, common envelope, supernova natal kicks, all based on just looking at these stars that have been flung across the galaxy. And I'm going to be doing that far away on the East Coast. I'm going back to New York. I'm going to be a Flatiron Research Fellow. There's going to be good stuff there. This was from the defense. I can skip this. And yeah, so that has been the journey that we've gone through. And I did have a whole acknowledgements thing in the defense, which I've skipped, but I kept this last slide because I enjoy it. So, wind's blowing, you're out at sea, you see me floating around an iceberg, and you just hear me talking about why binaries are really cool. What I pointed out in the defense is that there's actually a lot going on under the surface. And really, I couldn't have done this without a lot of people who kind of made it all work. And so thank you to them. Thank you all for listening. I'll leave you with a bunch of takeaways here and ask if you've got any questions. Go for it.
Our sun is axis is tilted 7 degrees from the ecliptic. Does that imply that it was once a binary system that merger kind of tilted its axis?
That can happen, and it can tilt axes in that way. But I don't think that it would do this in our system, because if you had any sort of merger, then it's going to be really dramatic for all of the planets that are around it. For like a dynamically stable system that has 8 planets around it, if you had 2 things merge in the center, then just everything's going to go flying. So I don't think that's the signature of that. Yeah?
The 29% of single planets, do they have a gradient of what ones are made of binary stars or anything like that?
Oh, so that is accounting for that situation. So on that pie chart, the 29% of the effectively single, there was a 24% that are the mergers. So those are ones where they were binaries and now they look like single stars. But those 29% will never merge. They will always stay binaries. Yeah. Yeah?
So when you use Cogsworth, are you running simulations with it, or are you taking simulations as input?
Both. So when I'm using Cogsworth, am I running the simulations or am I using others? So I will use those hydrodynamical simulations to choose where do I put the stars, what stars do I form, but then I will then individually evolve each star and also integrate its orbit through the galaxy. And it's nice because most of those things are independent, so it can be fully multi-processed, so I can take like 120 cores on the supercomputer and just like go wild. So for example, running that simulation on the Fire galaxy, it's like hundreds of millions of binaries, and it takes like 2 hours when I run it on 128 CPUs. So it's not too bad. And it's a whole galaxy of binaries, so I think it's not too bad. Hello, David.
So it looked like most of the really far stars that were going supernova were secondaries. So
Correct.
presumably that means they're less massive than the primary.
That is true.
Otherwise they would have lost supernova bursts. So you know if that preferentially form neutron stars in a measurable way, or do you expect the kind of proportion of neutron stars to black holes to be pretty similar? That's probably further out.
So it is true that the lower mass stars are the things that go far away, and the lower mass stars are more likely to form neutron stars. Was that a rat?
Did you see that?
Damn.
So in terms of like when they are at the moment of formation, yes, they would be further away. However, neutron stars are, well, actually, maybe this could work. So the neutron stars are more likely to get larger kicks. Black holes will have a situation where, yes, there was an asymmetric explosion, then you get a fallback of mass, which negates some of the asymmetry, so they get lower kicks. So your neutron stars will end up being much further away because of that. So it's less because of this region. That will dominate it on billions of years timescales. Short timescales, I agree. Oh, and once. Oh, several hands. Okay, at the back.
Do you or anyone else within the department look into triplets and quadruplets and the same things apply?
Yeah, awesome. Question is about triples and quadruples and higher order multiple systems beyond binary stars. I don't. I would love to. This is something I really want to learn more about. You can have very interesting situations. Often these things are hierarchical in that you'll have an inner binary and then a third star around it, rather than this like dynamically chaotic all sorts of 3 stars things, so they don't usually stay together. In that situation, the third star can kind of go around and drive the 2 ones inwards. It's something called von Zeipel-Kozai-Lidov oscillations. Yeah, fun words, right? It's just people. We shouldn't name things after people. I'm just going to throw that out there. And so you can end up with like more mergers because of that. So yeah, triples are really cool. I don't do them. I would love for people to do that. Maybe in the future. That'll be me. Once again, going once. Going twice. There it is. Thank you, everyone.
All right. Yeah, keep it going. Tom did a stellar job. Yeah. And Tom, I actually just, since you're leaving forever, I want to solve this once and for all. It's Z, beta, aluminum, and basil. Okay? I know. Yeah.
Never.